Hello, so I'm Brigitte Leridon and I'm going to introduce, I'm the CEO of PioniQ Technologies. I'm also a CNRS researcher and I'm going to introduce our technology which consists in using quantum materials for energy storage. So I don't know how to change this. So let me introduce PioniQ's team. On the left you have Clément Barraud, who is our Chief Operating Officer. Clément is a former quantum material physicist at Université Paris-Cité. He was also a scientific advisor for investors and CSO at Happy Electrons in the United Kingdom. Rémi Federici is our Chief Technical Officer. He's an expert of nanomaterials and processes. He's a former project leader at NextDot. And myself, Brigitte Leridon, so a quantum material physicist at CNRS and now CEO of PioniQ Technology. PioniQ is a very young company. It was just incorporated last December 26. So our vision stemmed from the general observation that the world needs massive energy decarbonation. And this will go into two main routes. One is the rise of electrical vehicles. In particular, European Commission has foreseen the end of thermal engine by 2035. The second route is to use a larger share of renewable energies in the mix, in the energy mix, but these renewable energy are highly intermittent, so they need energy storage solution. And this is in a context of rising Internet of Things with objects that are more clever, that are more connected, but that will require disseminated energy sources. So the experts state that the market will need more than 50% increase in the storage solution just in the next 5 years. So the leading technology for energy storage is the lithium-based technologies, batteries, lithium-ion batteries and lithium metal batteries, but they suffer from a number of serious drawbacks. The first one is that they use lithium, cobalt, nickel, that are critical resources that pose ethical issues and geostrategical and sovereignty issues. The specific use of lithium and sodium pose safety problems, such as we all have in mind cell phone or cars or buses bursting into fire. And when, for example, you have a lithium battery plant that bursts into fire, this poses also an environmental issue of toxicity for the environment. The fact that this system mostly uses liquid entails aging issues, absence of predictive models, and temperature limitation. So at PioniQ, we want to offer all-solid, lithium-free, cobalt-free, nickel-free, safe, integrable, and sustainable energy storage device. Actually, we want to design the next generation batteries. So to do that, we will use a double optimization loop. The first loop on the right is an optimization on the material itself. So we start from ab initio simulation. We do the material design, material synthesis, we measure the properties, and we feed the database with these properties. And we also consider a second loop by optimizing not only the materials, but also the devices. We go to designing devices, and then again measuring their properties and feeding our database. So the question is, why using quantum materials for energy storage solution? So quantum materials can be defined by the emergent concept that was initially proposed by Phil Anderson, Nobel Prize in Physics, in 1972, under the motto, more is different, which means that when you have an assembly of n quantum particles, properties emerge that cannot be trivially inferred from the properties of the one particle. So this very rich concept leads to material that have different degrees of freedom, and when these different degrees of freedom interplay, you have very interesting properties that are taken into account, for example, in different applications such as quantum computing, motronics, magnetoelectrics, and topological electronics. So I would like to add a fifth application domain, which is energy storage. And what we want to do as PioniQ is take advantage of the quantum materials to design energy storage devices. So, for example, we have identified the first family of crystalline material, and by taking advantage of their properties, we have designed a prototype for battery. And now we are targeting the performance here on my graph of to make a battery of millimeter size with energy density in the range 110 milliwatt per centimeter square and power density 110 watt per centimeter square over more than 10,000 cycles. So our competitive advantages are safety, availability of materials, and integrability. These batteries can be made on chip, they can be made very small, and they can be also incorporated into CMOS techniques. So our first targeted markets for these micro batteries specifically are electronics for IoT, electronics for defense and space. And in a second stage, we also want to target energy harvesting and mobility, but with more massive batteries, bulk batteries. So the market perspectives are very good because there have been estimated that the solid-state micro batteries should amount to a turnover of about $3 to $6 billion in the years 2030, 2034, and $6 to $8 billion for the bulk batteries, solid-state bulk batteries in the same years. So our partners are a number of academic partners in France and abroad. We're also discussing with, we have collaboration with other startups, and we are well embedded into the French innovation ecosystem with partnership with BPI France, Cantonation, PCA, par incubator, CNRS Innovation and PSL Valorisation. And I'd like to summarize. PioniQ incorporated just in December 26th. Our team is 3 co-founders, plus we are now hiring 3 PhDs to enrich our skill portfolio. We are incubated in the center of Paris at the SPCI Paris, in incubator PC Up. And we are now building use case with end users and industrial partners in order to convince the integrator of our technology. And with this, I thank you for your attention.
Thank you, Brigitte. Thank you very much. Very impressive. You're solving a very important problem. One question, what is your business model? So how do you see it? Do you want to manufacture batteries? Do you want to create IP that you license to manufacturers? Do you want also to design batteries on demand for some very complex, I mean, some technology companies, or the three of the above, or?
The 3, actually. So, for example, for the micro batteries, we envisage to fabricate them. But for the bulk batteries, we are more on the second business model, which is to license to manufacturers, but also to design customized devices for specific application, which will be probably very different depending on the sector.
Thank you. Your email address is still ESPCI. Are you full-time or part-time in the company right now?
So I'm 80% of my time in the company and still 20% CNRS for the next 2 years, and then I will be 100% in the company. And we have a license agreement that is being signed with our tech transfer, because we have patents, and we are now signing the license agreement, so it's part of the transfer.
And how much is your needs?
Sorry?
Are you raising?
So we have already raised about 2 million in pre-seed, and we are now looking for the next stage, the seed, so a few more millions.
What is inside these quantum materials? Are they difficult to manufacture? What type of raw material do you need in terms of atoms? Is it something, I mean, do we trade cobalt for something more also difficult to find, or is it carbon, things that are easy to find?
Okay, so these materials are precursor titanium dioxide, and they are oxide of either potassium or rubidium. So rubidium is more expensive than potassium, so we are trying to have a device that has more potassium than rubidium, and this seems to be successful. So titanium oxide is very cheap and affordable. It's not like titanium metal.
It's found in sunscreen.
Exactly, it's in any paint or any sunscreen, exactly. So this is very easy. We manufacture the crystal in the lab very easily. But now our next task is to miniaturize the layers, to pile up many layers to densify.
Okay, thank you.
Thank you, Brigitte. Thank you very much.